Right. Well, sorry we're a little bit late, but let's get started. So welcome to the first lecture on the lecture series called Future of AI, Foundation Models and Generative AI. This is actually the second year we hold this class. So I started working on this course before the recent hype and breakthroughs of ChatGPT. And I really felt that we're starting to see kind of a new approach to AI in the community that was really gonna change things for real. And I think we started to see that right now. And really what I want to accomplish in this lecture series is to give you an understanding of why this is happening right now, what's the underlying kind of change in perspective, and also going beyond just kind of the tip of the iceberg, which is ChatGPT. So I'm going to give you a deep but non-technical introduction to these subjects. Last year, when I gave this course, we were excited about text-to-video and text-to-image models, right? I guess we still are. We were excited about superhuman robotics, self-driving cars, and AI applied now to other domains as well, like genomics, etc. And of course, a lot of these breakthroughs, even if they're in very different domains, they come back to this underlying technological achievement of foundation models and generative AI. We're going to dive into. Last year, we were excited about ChatGPT, right? So we could ask it to write an engaging introduction to an AI lecture. If we ask the updated GPT-4, it produces more text, but maybe does a better job as well. Last year, we asked it to produce a engaging artwork of artificial intelligence. And now we're asking the newest version, it also might be doing a better job. It looks more involved at least. Art is subjective, but I think it's better. So if we were excited about these things in early 2023, what's happened, right? What's happened during this year? Well, a lot of things. Of course, it's been a tremendous hype. So there's been a lot of money pouring into these areas. We've had companies that are only a few weeks or months old reaching a $2 billion valuation with just a team of 5 people. We've had excitement about autonomous agents that we're going to talk about during this course as well, like GPT Engineer, that's able to plan and even act in a more human-like way in terms of intelligence. NVIDIA, that provides all the different GPUs, right, that these models need, have reached a huge valuation, like the $1 trillion club. We've seen sweeping regulatory kind of acts and initiatives, right, both from the White House and the European Union, for example. There's been a lot of drama in the AI space, right? OpenAI, for example, the CEO and the company behind ChatGPT, the CEO was ousted and then came back in. So maybe the transparency problem in AI doesn't only apply to the models, but to the structures and companies behind them. And also, we're seeing a kind of some hype and some winners in terms of these new AI technologies, but also now some companies are actually losing users and usage, right? Stack Overflow, for example, people saying that it's being killed by an AI that's trained on its own data, which is kind of ironic. Of course, one of the big questions that remain is, have we reached artificial general intelligence yet? Some people say we have. I think there's still quite a long way to go, but we're going to try to also explore a little bit, what can we actually mean with AGI? How could we potentially reach it, given the technology that we have right now? And can we give some kind of very order of magnitude estimation to when we'll get there? So I'm Richard. I was born in the land of Abba and Ikea, which is Sweden. Before MIT, I was at Stanford for 7 years, and I did research as well on AI and this stuff. I also started a company that does foundation models and generative AI in commercial settings. So I hope to bring in a little bit of those perspectives as well. For the last 4 years, almost now, I think, almost 4 years, I've been at MIT where I do research on self-supervised learning and foundation models and the good stuff. Okay, so quickly on the course schedule. So today we'll give an introduction and kind of a history of AI from a high-level perspective as well, what's going on, and giving some kind of intuition. And then in the next lecture, we'll dive much more into details about how these different algorithms work and how we arrive at these models that we use. After that, we'll do an in-depth analysis of ChatGPT, like a case study. Then we'll do a similar case study on image generation and stable diffusion. Then, right, and these 4 first lectures will be very similar to last year's offering. But then we're adding on January 23rd, we're going to talk about kind of emerging foundation models, right? It's going to be a combination of them existing out there, probably not one single model to rule them all. So we're going to talk about that, and especially how that looks in industry and corporate setting. So Professor Manolis Kellis will come, as well as, and he's an expert on biology and genomics, and then also Artem Sorkin, who's an MBA from MIT, and he'll talk about autonomous agents. And then we'll have a fun kind of, or it's going to be a fun, hopefully fun lecture on AI and ethics, which is, of course, perhaps a little bit more fussy, but we'll also bring in regulations, but kind of what's happening in terms of the institutions regulating AI. And after that, we'll also have a panel with Manolis and Artem. So it should be fun. All right, so what we'll cover? Well, we'll cover all the buzzwords. Neural network, supervised learning, representation, unsupervised learning, reinforcement learning, generative AI, foundation models, self-supervised learning. And we'll try to put together a lot of applications, a lot of intuition, because it really, should be non-technical. And I think as well, I want to try to explain things in simple but true, deep ways. And I think if you're not able to explain something in a simple way, you're actually not doing a good job explaining it. So that's what we're going to try to do at least. Today, we're going to give you a short, succinct answer to what is the secret sauce behind foundation models generative AI. And then when we've done that, we're going to ask, how's the world structured? Because how we think the world is structured really influences how we learn in the world. So we're going to kind of explore that from a more philosophical perspective and see how that actually leads us to foundation models and generative AI. And then at the end, we'll cover 2 applications of how we can use this in both research and in business. Again, right, we're going to try to use intuition, examples from both science and business. And hopefully you'll understand why the hype actually is real. I said it's last year, but it is real. And maybe also understand what's actually just hype and what's the kind of more foundational aspect of it, right? What matters. Okay, so I think in trying to understand and have a intuitive understanding of AI, it's good to use ourselves as a reference frame, right? We're human beings. And I think one of the core questions that we can ask is, well, at some point, right, you're born, you're a blank slate baby, fairly useless. You grow up, you interact with the world and different stakeholders in the world, and you acquire knowledge, and you become a fairly useful, knowledgeable adult, right? In terms of AI and learning, right, one of the key questions is, what happens in between you being a blank slate, fairly useless baby to you being a knowledgeable, useful adult? That's one of the key questions. And we're going to use ourselves as a reference frame here. So let's consider a few candidates that might be responsible for giving us most of the knowledge that we have about the world. Is it our parents? They give birth to us, they raise us, they give us a lot of our core values. So they're definitely good candidates to consider. Is it perhaps our DNA and our genes? They're responsible for giving us a lot of our physical characteristics, also some of our personal characteristics. But maybe it's nurture versus nature. It's very flexible. People can come very different based on where they grow up. And also maybe DNA works on a more generational scale sometimes. It's kind of a very delayed feedback loop here. It's not a lot of learning happening in a short-term scale. Maybe it's academia, right? Maybe it's teachers and professors and the educational system. It's supposed to be able to educate us. It make us useful, learn different skills, and also learn how the world works, right? So that's also a good candidate. And lastly, maybe it's more kind of our immediate environment, and what's more important is our goals, that we want to be loved, we want to be happy, we want to be successful. And by optimizing those objectives and goals, we learn about the environment in the process. We learn how the environment and different components in environments help or doesn't help us reach our goals, and therefore we learn about it. Okay, so we can split this apart a little bit more and high-level perspective see how they correspond to different disciplines within AI. Right, so this parent-child, student-teacher relationship, that's supervised learning. There's supervision. So here, there's a human expert, like a teacher or a parent, that puts the world in order for you. It structures it, it labels it, and puts it in a condensed format so you can learn from it. And on the other hand, this more delayed feedback, right, kind of evolutionary, and you're interacting with the environment, optimizing some goals, and those goals are what we're mostly focusing on, right? That's reinforcement learning. And that's this delayed gratification, and you're optimizing this goal in an environment. But it turns out actually that none of these approaches are responsible for giving you most of the knowledge that you have about the world. In fact, you can thank yourself for that, because most things you learn by yourself. So how is this possible? Well, it's possible by defining meaning by the company it keeps. So, and learning from observing the world. So let's take the example of a dog. You actually don't learn what a dog is from your parents telling you or from your emotions guiding you. You learn what a dog is by observing dogs in different contexts and correlating and contrasting dogs with other concepts. So a dog is something that's walked by an owner with a leash. It's something that has an antagonistic relationship with cats. It's something that chases frisbees when those are thrown. And this kind of relational context is what allows us to understand what a dog is. And as you learn what dogs are by correlating and contrasting dogs with other concepts like cats, for example, you in turn learn what cats are, right? This is where you get this relational understanding of different concepts. And even language can be learned this way because the word or name dog will be uttered more in context where dogs appear. And if you think about it, if a little child points at a dog and asks his parents, like, hey, what's that? Like, all the parent is really doing is giving some label. And the child having the ability to generalize that label to all dogs shows how it has a very, very robust understanding of an entity already, a concept of a dog, just not a name yet, perhaps. But that entity and concept is gotten by just observing dogs. So, for example, let's take the cat and mouse here. So I think intuitive for ourselves when we hear cat and mouse, there's a strong correlation, and we can understand a cat in terms of mouse and vice versa, right? A cat is something that chases mice, and a mouse is something that's being chased typically by a cat. But when it comes to a mouse and a dog, I think that the relation is less strong and less obvious, right? What's the relationship between a dog and a mouse? It's not completely clear in our kind of contextual understanding of the world. So let's take this observation and fit it into this foundation generative AI models that also have this similar understanding of meaning, right? So a lot of these, basically all the images you see in these lectures is produced by generative AI. So let's ask this generative AI text to image to generate a cat playing with a mouse, right? This makes sense based on how it's trained. It understands and generates a mouse, or a cat playing with a mouse in some sense. But if you ask it instead to generate a dog playing with a mouse, it gets confused because it doesn't really make as much sense in a contextual relational understanding that this model has of the world. So it generates a mouse-looking dog playing with a computer mouse. So this shows that when the context is not clear, meaning is not clear. And this is fundamental to how this model has started to learn about the world, and it also corresponds to how we think about it. Probably when I said cat and mouse to you, you immediately collapsed to a meaning space where it was obvious what a mouse was. You didn't even think about a computer mouse when I said cat and mouse because it just contextually made meaning clear for you. Okay, so basically, more relations leads to a better understanding of meaning. You understanding what love is, for example, helps you understand what a dog is, because an owner loves his dog. So, why not train a huge model with a ton of parameters that's able to compress a lot of these different relations on as much data as possible to learn as many relations as possible, right? So you get the most precise understanding of all of these distinct concepts involved, and then you use this model basically anywhere where any of these concepts appear, right? And that's exactly what a foundation model is, rests upon. And somehow also, your brain is a prime example of some kind of foundation model, where you get a world, model and knowledge model about the world from just observing it and building these relational structures. And this is also what's behind this current AI revolution that we're seeing. This is the building block that is fueling all of the different breakthroughs that we're seeing right now. Okay, so this might sound kind of intuitive and make sense, but why did it take us such a long time to get here? Well, this is where I think is quite useful to go on a little bit of a philosophical digression, and provide a little bit of my theory or picture on how this happened, and also it's shared with other researchers, some of them. So I think this kind of rests a little bit on two kind of opposing perspectives about how the world is structured and how we learn in the world. So I'm going to try to get a sense of this by giving some examples and contrast some stuff. So on one hand, we have learning versus designing, where designing is this, like a clockwork. We know how every piece works. We put them together. Every piece has like a perfect role to play. We know what's going on, and it's built with a specific blueprint and purpose in mind, right? That's how we design things. On the other hand, learning is something that we perhaps not fully understand and we're not completely conscious about. It just happens. We just get better at something as we're exposed to the phenomena more and more and more. And there's really no, end goal in mind before we start learning, right? We just adapt. And it's very, very flexible and intuitive. Okay, similarly, we have chaos versus order, where order is kind of what exists on the scale of planets or atoms, where things behave according to beautiful, simple rule, like math, physics, and beautiful theory, right? What chaos is perhaps, the more unpredictable reality that we find ourselves as human beings, right? The animal world, the human world, where things are unpredictable and chaotic. And one of the core questions here as well is that, the chaos that we experience in our everyday life, is there some simple order behind all of that? If you just find that order, will all of our experience make sense? Or is there perhaps a limit to the order of the world and how much equations actually can explain? And do we have to deal somehow with this chaotic world in another way? Similarly, we have this perspective of bottom-up and top-down, right? In a top-down organizations, there is a boss or some top person that's able to come up with a nice framework for how things should be done from the top, just by analyzing data, and then push that throughout the organization to everybody involved somehow. On the other hand, a bottom-up organization it's really necessary to have a lot of people at the bottom that interacts perhaps with customers and products and deals with all this different chaos that happens in all the particulars. And there's no real simple top-down decisions that can be made to make your business really work. You need to account for all the particulars, and it really matters how you engage with a customer on a personal level. It's not enough for the boss to come up with some 10 simple rules for how to solve these things. You need to deal with this chaos. And also a lot of the wisdom in a bottom-up organization comes from really listening to the people that are closest to the end consumers. Okay, so I think, at least in the Western world, we have had for quite a long time this designing ordered top-down perspective. And I think this is kind of due to the ancient Greeks, right? So Socrates, for example, had this allegory of the cave, where basically human beings have very imperfect senses and a very kind of imperfect understanding of how the world really works and what's going on. And they give this allegory of the cave, where human beings are actually here on the left-hand side, looking, at the reflections of the cave. So basically, our experience of the world is so untrue and imperfect, so we don't even get to experience the world firsthand. We get to experience gods walking with depictions of real objects, right? And we don't get to see those even. We get to see the reflection of those depictions through, a fire on the cave wall. That's how distorted our view of reality is. And for Socrates, it's like, well, we have to accept that we have very distorted, imperfect experience of the world. We have to always strive to understand the real, true world, the beautiful world of the gods, which exist, outside of the world we get to experience. So I think for Socrates, a dog, for example, there is a true perspective of a perfect dog in this godly world that we should try to understand. And all the variations that we're seeing in the real world are just some kind of imperfection from our sense. And we should try to understand the true dog in this perfect, absolute world. So also, I think it makes sense because the Greeks at this time, they were discovering mathematics. And in math, for example, there exists a perfect circle that obeys very, very simple equations. But every time you take a perfect circle and try to recreate it in the real world, it's always off. It's always imperfect. So this kind of correspondence somehow influence Socrates' thinking and also makes sense in this kind of mathematical perspective. And I think this has been extremely fruitful for us. It's led to the kind of golden era of design. We've had a scientific revolution and an industrial revolution, right? We've had modern math, physics, and modern medicine. And we even went to the moon with this design way, top-down order way of thinking. So it's been extremely, extremely good for us. But, assuming that this top-down order design way of thinking is the be-all of our existence, how come we're not better at it? Right? We've had billions of years of evolution here on this earth. How come we're not more like a computer or a calculator? Right? If we can just try to find the simple mathematics and order behind the world, and we'll be able to perfectly exist in it. And I think this is kind of a strong indication that there actually is a limit to what order can explain, and we're not intrinsically very good at logic and math, because we don't live in a top-down order world. We live actually in a bottom-up world of chaos where math is not that useful. Instead, in a bottom-up world of chaos, what's useful is intuition, flexibility, and speed. The things that we actually are good at, right? So in this order versus chaos perspective, when it comes to our everyday interaction as human beings, besides the scale of planets or atoms, actually the world is chaotic, and we cannot escape that fact. We have to deal with it. There won't be some just simple equations that explain everything for us that we can rely on. We have to deal with all this chaos. There is somehow unavoidable. So what can we do? Right? Should we just give up? So is there an instrument that can help us to contain and navigate all of this chaotic world that we find ourselves in? Well, if we had billions of years of evolution and we didn't create a computer or calculator, or nature didn't, then what did it create? Well, it created the brain, which is our best tool of navigating and making sense and learning in a world of chaos. And then the neural network in artificial intelligence is just our best attempt of replicating the brain inside of a computer. Right? So it's very, very flexible and adaptive. It consists of a ton of kind of neurons or parameters. And it's very, very simple computations, but done in a hierarchy and scale. And also it's extremely slow to train, but very, very adaptable and flexible, and fast to execute when actually it's learned something. Okay, so we now have accepted the world as chaotic, and we have a tool that's able to still function and navigate in a chaotic world. How do we use this? Well, the thing is that these neural networks still exist inside of a computer, right? And a computer only speaks the language of code and math. So still, there is a divide now where we have the real chaotic world and we have a computer side of machine. So we somehow have to go through the world of order and math to tell the brain inside of the computer what to optimize for, or what to focus on, right? To use its brain for. We have to somehow describe this in a more exact way for it to be useful. So we can't still completely ignore the world of order. So how can we define such objectives rigorously? And that's what we're going to try to go through right now. So first thing we can do is to say that, well, we understand how the world works, right? We understand how things work, and we have a lot of knowledge about the world. So why don't we just impart that knowledge onto computers? Why don't we just structure the world in a way that makes sense for a computer? We'll label all of it, and then we can feed that information to a computer so it can start learning from that. Right? That's our first attempt, and that's supervised learning, where we structure the world, we label it, and so computers can learn from us. And pretty immediately we run into some problems. First off, of course, this scales with human labor, human experts, and labels. That's why you have these outsourcing centers where people label data constantly. And can everything even be labeled? Like, are we that kind of self-conscious about, are we that conscious about how things work? Like love, for example. Can we label concepts like love? It's probably going to be quite hard, and we maybe overestimate our understanding of how things work and how we can isolate concepts. And really, maybe things, again, like love or other things, are not very labelable, and maybe things are not as categorical or like distinct. Maybe the world is actually more continuous in a sense. And only in the limit of unlimited number of labels do you actually start to understand how the world is really structured. Right? Maybe I have a set of labels and you learn from them, but you will always find these points in between where labels don't really explain what's going on. For example, here, right? Is this a dog or a cat? The left-hand side. I mean, somehow at some points things get more and more close, and we'll reach a limit to how much we can label the world, and then we just need more and more labels to actually make sense of it. So because of this, somehow we see that the supervised learning doesn't by itself generalize well enough. It just doesn't work enough. It's too expensive in terms of having human people and experts label data. It doesn't generalize really well to the diverse setting of the real world. Okay, so let's say now that we try to rely on ourselves, defining things, structuring the world, and we do almost the opposite direction. So we say that as human beings, we have goals, we have desires that we want to optimize, or that we do optimize, and we hope that if we just impart those goals and desires onto a computer, it will learn about the world in the process, right? Focus on the endpoint, like where you want to end up, and the computer will have to figure out how to get there. So this is reinforcement learning. But I think if a good analogy for a blank slate computer is like a blank slate baby, I think it's very, very hard for us to even understand what it means to be a complete blank slate. I think a lot of our knowledge is so intuitive, we just take it for granted. So what does it actually mean for something to be a complete blank slate? Like having no understanding of how the world works at a starting point. So let's say you're this blank slate baby, and no understanding of how the world works, and you want to optimize certain goals. Right? Maybe you want to optimize success or becoming rich. Right? First of all, there's a huge delay in the feedback. Right? You do something, you won't immediately know if it's actually helping you or not. So you have to wait a long time before you get a signal. Right? So it's very, very difficult to know what's working and not. You need to keep at it for a long time before you see that it makes a difference. Right? But even if you take something that's perhaps a little bit more immediate, like trying to become less hungry, it's still some delay in terms of maybe minutes or something. But let's say you try to reduce your hunger, right? But you have no understanding of how the world works. You just randomly pick a concept that you're observing, and you start to explore how that concept affects your ability to become less hungry, right? To become full. Maybe you just start focusing on the moon and how the moon and the characteristics around the moon affects your ability to become less hungry. Right? You're gonna spend so much time exploring complete nonsense that has basically no relations to your ability to become less hungry, and you're gonna die out of hunger way before you make any progress whatsoever. So I think that's kind of hard to even understand. Let's take the example of a car that's a complete blank slate. You want the car to learn how to drive to your home using reinforcement learning. I mean, again, maybe it starts exploring how the moon affects the ability to reach home, and it will make no progress. But even if it starts focusing on things that are actually relevant by just sheer coincidence, and it starts focusing on other drivers or other human beings in traffic, right? Still, we cannot afford the car to hit like 1,000,000 human beings and crash 1,000,000 times before it actually reaches home, gets some signal, and starts making some progress, right? This is too expensive and too risky in real life. If you take, imagine putting a real baby in the driver's seat of a car. I mean, how many billions of years, if this baby would live forever, how many billions of years would it take for this baby to just by coincidence reach home? I mean, it's going to take forever. And then when it does that, you say like, hey, good baby, awesome work. Here's your signal. Now do it again. I mean, this is somehow how reinforcement works when there's just a delayed feedback and there's a blank slate. And this works better in chess or something where there's an idealized set of rules and the state space is much smaller. But this kind of just blows up in real life. So what we need is a basic model of how the world works that we get from just observing the world, because it's the only thing we can really afford. Right? Reinforcement learning, as we just said, is too dangerous. You'll die before you make any understanding of how the world works. And so it's too risky and too expensive and too slow. And supervised learning is also too expensive because it relies on human experts to label the world. And at the end of it, it doesn't work because you cannot label the world. Okay, again, so what comes to rescue is this breakthrough behind foundation models called self-supervised learning, where we learn from self-supervision by just observing the world. And we define meaning by the company it keeps, which allows us to learn from just observing. Okay, so quick recap. We talked about chaos versus order, and we concluded that actually the world is chaotic. We cannot ignore that. We have to deal with that. The brain is the best tool that we have to learn and compress and navigate in a chaotic world, but we still have to define how this brain should interact with the world. Supervised learning didn't work because it's too expensive and doesn't generalize, like labeling the world. Reinforcement learning is too dangerous and too slow. So that's why we end up with learning from observation and self-supervised learning. Okay, so let's dive into some specific use cases of this. So here's a kind of a collection of different self-supervised learning algorithms and how they learn from data, from just observing the data. We'll cover all of them in subsequent lectures. But what they all rely on is learning from data itself, right? There's no need for human experts in the loop. So it scales extremely well to unlimited amount of data. And then they use these very broad capabilities in a wide range of different tasks. And in this lecture, we'll just talk quickly about predicting the future and positive pairs. Okay, so this idea of learning by predicting the future based on the past relies on this idea that in order to predict the future, like we need to understand the past. So let's take an example of language model or learning, learning from text data. So this is good because we have an unlimited basically amount of text data from the internet. So we can just download a sequence of text and then we can remove the last word and try to predict the last word based on previous words. It is extremely simple to define, and then we can let the huge brain of a new network start doing this task. And let's now assume that this new network or computer has become really, really good at predicting the next word based on previous words. What does that actually imply? What does it learn? Does it learn grammar? Well, in order to generate and predict grammar, like grammatically correct sentences, it has to understand grammar, of course. I mean, does it have to understand the meaning of words? I mean, if the sentence that we give it is, the dog is, it needs to understand what adjectives that describes a dog. So it also needs to understand the meaning of words. Does it have to understand the difference between a informal social media post or a formal news article? Well, if it's right now being fed a informal Facebook post and it wants to complete that accurately, it needs to understand what kind of language that corresponds to, and vice versa, right? And similarly, like if the way people write changes based on their political beliefs, they also needs to pick up their political beliefs based on how they write things, right? Which is only where it gets kind of scary, but a really, really powerful model can start picking up those things that are so implicit because it's optimized to do this fairly simple task. And again, if I ask it, what's the capital of Stockholm what's the capital of Sweden question mark, right? And I give that sentence to the model, and it has to complete it accurately and optimally. It has to give the correct answer, which is Stockholm. So it also becomes very knowledgeable about the world in a bigger sense. And this is the core, approach behind ChatGPT and why it works so well and why it's so flexible in capabilities, right? And how such a simple objective can lead to extremely, broad sense of intelligence. And again, similar things applies to real life. For example, like frames in real life or in a movie or something, right? If a model is able to say that, okay, it sees a human being with a leash and a dog, and in the next frame it sees a frisbee, if it's able to predict then and say, well, probably the human being will throw the frisbee and the dog will run to catch it, right? Being able to do that prediction to combine these objects show that this model understands how these objects relate to each other. So it's extremely, extremely flexible and powerful. Okay, another approach that's very popular in vision is called positive pair or contrastive learning. Here we learn, here again we can just say that we think that objects that appear in the same image are more related than objects that appear in different images. So then we can just download a ton of images from online, and we can just kind of randomly crop the images and push the crops from the same image close together and far away from crops from other images. And if we do this, we're going to see like, well, okay, so a human being, this on the left-hand side, right, the crop here with the human being, a leash, and a dog, is going to push a dog kind of closer in meaning to a human being with a leash, and a dog and a frisbee being pushed together somewhat because they're more related. But also the really, really cool thing here is that it kind of rests on this assumption as well that you don't even have to appear in the same context to be understood. It's like people that have similar friends are similar people. So here again, like, okay, the frisbee and the human being in the leash don't appear in the same image, but they appear together with similar objects like a dog. So somehow as well, it will start to capture the relationship between these, which can be kind of more abstract and more isolated, like more far away in some sense, but it still captures that in a very robust sense. Okay, so let's apply this. So we're going to talk from one example in science and another in business. Okay, so let's say we want to apply this new paradigm to genomics. It's a good setting because we have a abundance of DNA base pair, like this, basically these text sequences that we get from sequencing people's genomes. So what we've done and what we could do is that we could use our own human intelligence and look through this data and see like, well, there seems to be these reoccurring sequences, like genes, for example, that reappear. And we can look at these evolutionary trees, how these things are being passed on, etc., to build up a structure and start building features around parts of the genome. And then use that for example, protein structure prediction, like to start understand how the genes work. Or we can just kind of rely on self-supervised learning and just try to predict the next DNA-based pair letter based on previous ones. So let's say we train a huge model on a ton of DNA data to just predict the next DNA-based pair based on previous ones. Like, what does it learn in this process implicitly? So if it's able to do this really, really well, like again, does it learn the meaning of genes and genes? Yeah, so genes are just reoccurring sequences. So if it's wants to be able to complete this the genetic sequence really, really well, it needs to understand, like, identify, hey, I'm inside of this gene right now, and that's why I need to generate these new letters, right? Does it need to understand as well implicitly if it's kind of completing the genome of a dog versus a cat? Yes, if they differ, it needs to, because is it going to change how it thinks about predicting the next base pair? And it turns out it actually creates really, really good features that maybe it takes us some time for human beings to actually understand exactly what they encode. But if you then use these features and you train another network to predict protein structure, right? What kind of protein structure this DNA will lead to, it works really, really well. Okay, another example in the business case that I was involved in my startup, here, let's say you come to a retail company and they want to understand their consumers and maybe have a better assortment and give recommendations, etc. So typically what they do is that they come in taking some consultants to start trying to define some user profiles, right? If it's young single people or families with kids, and they try to build that up and kind of label people and consumers. And they do a lot of questionnaires and stuff where they ask customers like, hey, who are you? What do you prefer, etc., to build up some kind of knowledge structure. So first off, right, there's a problem because every human being is unique. So every time you enforce some kind of user profiles, you typically lose a lot of actual understanding and performance of your models because they rely on very, very coarse information and structure. And also, it's actually very, very hard to ask people what they want and how they work because they are not completely self-aware of what makes them make a certain decision and what they would prefer. And it takes also a lot of work, like a lot of manual work to map up all these people, ask them questions and questionnaires to start to build up this understanding of your consumers. So what we can do instead is start to kind of look at the behavior of the customers and let the customers do the work for you by just acting in your channels, right? And tracking some of their interaction points. So here, for example, right, we have on the top, somebody buying a wine bottle, a cheese, and some chocolate. And if the model is kind of good at understanding and predicting, for example, the next step of a consumer, it can say like, and in the bottom we have a soda and a candy. It can perhaps start predicting like, okay, the top person is an adult or something that wants to relax on a Friday night, and the bottom is a child equivalent version. And then if it looks at some behavior of a family coming into the store, it can kind of recommend both maybe, because if it's a family, it has somehow both of these features. And this, like, the capabilities of these models when you train them enough data becomes extremely sophisticated, and it's very, very cheap to track data rather than building up all yourself from human work. And also, right, some of what this eventually gets to is a more deep understanding of your consumers, like your products and the customers, right, how they interact. And if you're in retail, that's basically all of your business. It's understanding your products and your customers and making the best combination. So then as you start building up this understanding, it can use it in a broader sense across the company for business intelligence, etc. So also by building a more deep and general intelligence, make it more applicable broadly in the company. Instead of approaching every problem in isolation, which doesn't scale that well. Okay, so to summarize, we started with a short answer to like what's the core fundamental change in perspective behind foundation models of generative AI, right? Learning from observation. We start to ask like how's the world structured? Chaos versus order, top down versus bottom up, design versus learning. And we said there is a limit to order and design, and neural networks are a way to compressing and dealing with this chaos. But as we define these different objectives, we still end up with self-supervised learning and learning from observation as somehow at least what we know now, a viable option forward. We have to learn from unlabeled data directly and learn from observing rather than interacting, because that can be too dangerous and expensive. And then we also cover two applications, one in science and one in business. Okay, and I want to leave you with this picture, I think. Right, the meaning is relational. And also maybe ask yourself, like, do you have implicit self-supervised learning algorithms going on in your own head? Right, this is how you learn. If I would take this clicker, for example, and I would just drop it and it would float in the air, I mean, you'd probably be upset or even, surprised and upset that this is happening. Like almost subconsciously, because you probably have this mental model in your head that's always trying to predict what's going to happen next based on previous action, right? And by doing that and slightly adjusting when you observe the world, you implicitly learn about the whole world in the process, right? You have these algorithms going on in your own head. Okay, next lecture, we will make this much, much more concrete. We'll go through different algorithms, and that should be very, very exciting. We also have a website, futureofai.mit.edu, where you can get all the updates and other good stuff. So thank you super much, and if you have any questions, feel free to ask.
Yeah, I got well like the intuition on the first two models that you said, but in the case of like the self-supervised models, it didn't really get like the intuition behind it.
You got the intuition of the two first, predicting the future and positive pairs. Did you understand the intuition there a little bit?
Yeah.
But you didn't understand self-supervised learning.
Yeah.
That's exactly self-supervised learning. Those are two examples of self-supervised learning. So I mean, actually, the first time we offered this course, it was called Foundation Models and Self-Supervised Learning. So self-supervised learning is how you train foundation models and generative AI, right? Foundation model and generative AI is the output. So those two examples are self-supervised learning. So self-supervised learning is a family of algorithms that give you generative AI and foundation models. Does that make sense? So I think maybe, yeah, pointing that out is important because self-supervised learning is the approach and how we train these models, right? And when we train them, we call them foundation models. So ChatGPT is trained using self-supervised learning. So it gets a little bit technical. I mean, if you had like Jan LeCun, for example, he said like, oh, just call it self-supervised learning. Why call it foundation model generative AI? But then it's like, oh, let's call it foundation model because that's more sounds better than what it is, and there's some definition from Stanford that they use. But then the media is like, well, generative AI sounds cooler, and stuff like that. So there's terms as well that are different based on the context. But all those two examples you understand are self-supervised learning. That's examples of it.
Thank you.